Yeah, so just summarizing what we just said, A is the matrix then of eigenvectors, obviously here, yeah, as we just said, and S is the squared matrix, or the matrix of the squared eigenvalues. Yeah, so A is the matrix of eigenvalues, eigenvectors, eigenvalues of the covariance matrix are the squared singular values of D. So eigenvalues and eigenvectors of the covariance matrix, or basically, yeah, of the covariance matrix can be determined by SVD, the application of SVD on the covariance matrix, not on the data matrix. So SVD is a method to perform PCA, just as we did it here. Yeah, so we just apply SVD on the covariance matrix, like this one here, and yeah, then actually get the corresponding PCs. Yeah. Okay, so and why should we do that actually? Well, I told you that SVD is a generalization of PCA. We talked about that, yeah. And why should it be better to, or sometimes why should it be better to perform PCA by using SVD or by computing the SVD? Well, sometimes, especially for large dimensionalities, SVD is much more stable than PCA, especially if you have a lot of dimensions and a lot of sparse dimensions. So, for example, with text data, SVD is better or more stable than PCA, and especially SVD can cope with dependent dimensions, yeah, which is sometimes a little bit a problem with PCA. I mean, in PCA, it is a kind of special case that we have dependent dimensions, yeah? And in SVD it's the normal case. Yeah? So in SVD we assume, so to say, or SVD assumes that we have that the rank of the data matrix is smaller than D. Yeah? So K is smaller than D is the normal case in SVD, and in PCA that is typically the exceptional case. Yeah? So that's why SVD can be sometimes more stable than PCA. Yeah? By the way, SVD, and that means also PCA, as we just saw, can be formalized or reformalized as an optimization task. Yeah. And that is how that can be done, and that is basically the way that people compute it. Yeah. Optimization task means that it doesn't find the perfect solution, but it tries to find a very good solution actually. Yeah. So how is that done? Just that you see it. Well, the data matrix, as we said before, can be decomposed by the singular value decomposition in these three things here, where we just saw that S is the eigenvalue matrix basically. Yeah. So if we rewrite this OS A transposed a little bit into, well, we just use, instead of S, we use the square root of S squared, yeah, since S is a diagonal matrix. It doesn't play a role. So if we just multiply that the square root of it, it gives us S again. Yeah, so we take O times the square root of S times the square root of S times A transposed, and since S is also the square root of S is a diagonal matrix, the square root of S times the square root of S gives you S. Yeah, so that is the basic idea of this rewriting here. That's the same as here. So, and then we consider O times the square root of S as U, and the square root of S times A transposed as V transposed. Then we have rewritten the whole thing as U times V transposed, and now we can formulate with this reformulation the optimization problem, because we want to minimize the so-called representation loss. Yeah, so we get the original matrix. So U times V transposed should give you the original matrix, of course. Yeah, and if we approximate U times V transposed, we want to approximate it as best as possible, meaning that it should be as close to D as possible. Yeah, it should be as similar to D as possible. So how can we actually measure the similarity between two matrices, well, we can use the so-called, well, we can take the subtraction and use the so-called Frobenius norm, which is an n times, well, the Frobenius norm just sums up all the individual values in all the individual elements, or the square of the elements in a matrix. Yeah, so this is the squared Frobenius norm. The Frobenius norm would take the square root out of that, but we take the squared Frobenius norm, which is the squared here, yeah, which takes, well, first of all, of what? We take d minus u v transpose. So in the best case, that would be 0 for all entries in the result of this subtraction here. So in that case, the Frobenius norm would give you the sum of a lot of zeros squared gives you 0. Yeah, so we want to minimize this loss here, because this is the representation loss. This means how similar is uv transposed to d. Yeah, the similar it is, the smaller this representation loss is, obviously. Yeah, and yeah, we need some side constraints, because we need, of course, this orthogonality constraint in both cases here. So we need all the entries in the V's, in the V transpose, and all the entries in the U to be pairwise independent, pairwise orthogonal. So we need these side constraints here for the minimization problem or optimization problem in that case. Yeah? So SVD, and in that case also PCA, can be rewritten as an optimization task, which is typically solvable much faster than the exact solution, which is also prone to numerical errors, rounding errors, and stuff like that. So typically people apply this optimization problem in order to compute singular value decompositions or PCA even, because this can be done much faster. It's not the perfect solution, not the perfect solution, but it should be close to the perfect solution, of course. No? Okay, so that was actually singular value decomposition as a kind of expansion or extension or generalization of PCA. And now let's going back to PCA again and talk about kernel PCA. And for what it's that good for, actually.